Today we discuss about thermodynamic probability and total probability distribution. Here we derive the relation for thermodynamic probability and total probability distribution. Firstly, we discuss priori probability, and that priori probability shows that if all distribution of balls among the cells are equally probable and the size of all cells are same, then the priori probability is same. Here we find another term, thermodynamic probability, which denoted by M. Thermodynamic probability of a macrostate is defined as the number of microstates corresponding to that macrostate. Now, how we get the number of microstates for a particular macrostate, that we discussed earlier by taking one example of 4 phase points when distributed in the 2 cells. Now, just see here in the same article thermodynamic probability, we have to find the number of possible microstates for that macrostate. Hence, we are considering a box. That box is divided into number of cells. That cells numbered as 1, 2, 3 up to k cells. And in that box, n balls are distributed. If n balls are distributed in the box, then how many balls falls in first cell, second cell, third cell up to the kth cell, that we calculate here. And then we find now how we get the number of ways in which the particular number of balls falls in first cell, similarly second cell, third cell, and so on. The total number of ways gives thermodynamic probability. Now see here, if we select n1 balls out of n balls, those falls in first cell, then how we find the number of ways in which n1 ball out of n ball falls in first cell, that we discuss one by one here. Similarly, the n2 balls, if we select the n2 balls out of remaining balls, earlier we select n1 balls out of n balls, then how many balls are remaining? N, capital N minus n1 balls are remaining. In that remaining ball, we have to select n2 balls. Hence, n2 balls out of remaining balls n minus n1 when falls in the second cell, then we have to find how many number of ways we get the n2 balls in second cell. Similarly, n3 balls. n3 balls also we select out of the remaining ball. Earlier we select n2 balls out of n minus n1 ball. Hence, how many remaining? N minus n1 minus n2 balls are remaining. In that remaining ball, we have to select n3 ball. Hence, n3 balls out of remaining balls n minus small n1 minus small n2 balls when falls in the third cell, then we find the number of ways for the third cell. In that way, up to the nk balls out of remaining balls. Then if we select nk balls out of remaining balls may be n minus n1 minus n2 up to nk minus 1. When nk balls falls in these remaining out of remaining balls in kth cell, then we also find its number of ways. In that way, firstly we finding the number of ways for selecting n1 balls out of n balls may fall in first cell. That number of ways we write by using a combination rule. That combination rule we write out of n. How many we select? n1. Hence, n1 balls selecting out of n, then we arrange number of ways we write n factorial divided by n1 factorial into n minus n1 factorial. Now this is the general formula for selecting n1 balls out of n balls. Then these are the number of ways. That number of ways we write total number of balls n factorial divided by, in that total number how many we select, n1, hence divided term we write n1 factorial into remaining terms. If we select n1 balls in capital N balls, then how many remaining, capital N minus small n1 are remaining. Hence combination rule we write n c n1 equal to n factorial divided by n1 factorial into n minus n1 factorial, and we say this is the equation number 1. In that way we also find the number of ways for selecting n2 balls in second cell, but n2 balls we have to select out of remaining balls. How many remaining, n minus capital N minus n1, these are the remaining balls. Hence again we write the combination rule, this n minus capital N minus small n1, these are the remaining balls. Out of the remaining balls we select n2 balls, hence n minus n1 c n2 equal to capital N minus n1 factorial, this is the numerator term, divided by how many select, n2 factorial into remaining balls. Again if we select n2 out of n minus 1, then how many remaining, n minus small n1 minus n2 remaining balls. Then we write denominator term we write into remaining balls factorial, that is n capital N minus n1 minus n2 factorial, this is the second term. Similarly for third cell, if we select n3 balls, out of remaining balls are n minus n1 minus n2 factorial when they fall in the third cell, then we write the combination rule, capital N minus n1 minus n2, these are the remaining. In that remaining balls, out of that remaining balls we select n3 balls, therefore it is combination rule, we write n minus n1 minus n2 factorial divided by selecting, how many select, n3 factorial into, if we select n3 out of the remaining ball, then again remaining term is n minus n1 minus n2 minus n3 factorial. In such a way we considering all balls, means nk balls when falls in the kth cell out of remaining balls. Then we write its total number of ways in which all balls may falls in first, second, third up to kth cell. These number of ways are, gives its total thermodynamic probability. That thermodynamic probability denoted by m, that equal to product of the number of balls, n1 balls when falls in the first cell out of capital N balls, then it is given as equation number 1 term, n factorial divided by n1 factorial into n minus n1 factorial into second term. Second term is related for n2 balls out of n minus n1 balls when fall in the second cell. Its combination rule, n minus n1 factorial divided by n2 factorial into n capital N minus small n1 minus small n2 factorial. Similarly for third cell, we have to select n3 ball out of capital N minus n2 minus n1 minus n2 factorial. Then how many remaining, capital N minus small n1 minus small n2 minus small n3 factorial. Therefore the third term we also get. In that way up to the kth cell into k cell. We write here the even nk balls out of n minus n1 minus n2 up to nk minus 1 when fall in the kth cell. Using the combination rule, the last term is n minus n1 minus n2 minus up to nk minus 1 factorial divided by nk factorial into n minus n1 minus n2 minus n3 up to nk factorial. Now we simplify this term. How we get? n minus n gets cancelled. N minus n1 factorial, numerator denominator cancel. Here that is also gets cancelled. In the similar manner, here this term cancel with the next term, and remaining term we write thermodynamic probability m is equal to n factorial divided by, only remaining term is n1 factorial. For second term remaining term is n2 factorial. For third term remaining term is n3 factorial, and for last term up to which term is remaining, nk factorial. Hence that equation represent a thermodynamic probability, and that equation we call equation A. Hence equation A is it represent thermodynamic probability. Thermodynamic probability. That thermodynamic probability, it gives the number of possible microstates corresponding to a given macrostate. That we get n factorial divided by n1 factorial into n2 factorial into n3 factorial up to nk factorial. Now then we find total probability distribution, that is denoted by capital W, and it is defined as total probability distribution, which is the product of thermodynamic probability and priori probability. Now we write the direct relations which we derived earlier. M, equation A is known, that is n factorial divided by n1 factorial into n2 factorial into n3 factorial up to nk factorial into the priori probability. That priori probability is g1 raised to n1 into g2 raised to n2 up to the gk raised to nk. Now we simplify that relation. Here n factorial we keep as it is. Here g1 raised to n1, g2 raised to n2, g3 raised to n3 up to gk raised to nk. This is the product terms. Hence instead of this 1, 2, 3, g1, g2, g3, we write the product I is equal to 1 to k, gi raised to ni, since I equal to 1 to k. If we substitute I, we get g1 raised to n1 into g2 raised to n2 into g3 raised to n3 up to the gk raised to nk. This symbol pi, I equal to 1 to k, it stands for the product term or multiplication term. Similarly, the denominator term we also write in the product term symbol I equal to 1 to k. This is 1 divided by ni factorial, since n1 factorial, n2 factorial, n3 factorial up to nk factorial, that is I equal to 1 to k. This is ni factorial. Hence the simplified term for total probability distribution is given by this equation B. That equation B is here n factorial into I equal to 1 to k gi raised to ni divided by ni factorial. Now what is the factorial term? That factorial term we write up to the n factorial. How we write the n factorial? This is 1 up to, we write 1 into 2 into 3 up to n. Hence we write n into 1 factorial. Since we start from n minus 1, n minus 2, n minus 3 up to the 1. We write here. Hence this is the n factorial term generally we writing here. Now here we say that if n balls gets distributed, this pi product is the product of the term or multiplicative term for the values of I equal to 1 to k. Now then we see that if all balls falls in the box somewhere, then what is its total probability? Then you know that total probability is always equal to 1. That total probability is always equal to 1. If total probability distribution is 1, then what about the priori probability? That is 1. That we have to prove earlier. Hence, how we get? If priori probability is 1, that means total probability distribution is equal to 1. That we prove here. For that, we use equation B. We take the summation of both sides. Now, what is the summation on both sides? If we take equation B, summation, that is summation W equal to n factorial, since n is constant. With this again we cannot write again its summation, since n factorial is, we write its summation, that is summation of product term I equal to 1 to k gi raised to ni factorial. Now here this total term on this one side of the equation, that we use directly from multinomial theorem. Now what is the multinomial theorem? That multinomial theorem we write here. Multinomial theorem is summation xi to summation xi raised to n, means x1 plus x2 plus x3 up to xk raised to n. That is equal to, what is on the multinomial theorem? See here, summation ni means all values are in terms of n. This n1, n2, n3 up to nk. Hence we write the ni equal to k up to k. We write the n factorial divided by summation n1 factorial into n2 factorial up to the nk factorial into x raised to n1, x1 raised to n1, x2 raised to n2 up to the xn raised to nk. Here in that term, how the one side is equal to summation gi raised to capital N. How we get? Now see here, summation ni is capital n factorial. Summation n factorial means capital N factorial. Here summation 1 divided by n1 factorial, n2 factorial, n3 factorial means summation product 1 divided by ni factorial. That is also term here. Summation into product, summation into product gi raised to ni means x1 raised to n1, x2 raised to n2 up to the xn raised to nk. Hence the one side of the equation that is directly equal to summation gi total raised to n. Hence we write directly summation w is equal to summation gi raised to n using this multinomial theorem. Summation I equal to 1 to k gi raised to n. Hence summation gi means g1 plus g2 plus g3 up to gk raised to n. We discussed earlier priori probability. All probabilities are equally probable, means g1 is equal to g2 is equal to g3 is equal to g3 up to the gk. Hence what is the bracketed term? That is equal to 1. We write 1 raised to n, that is equal to 1. Hence the total probability distribution equal to 1. What it indicate? What it indicate? The total probability distribution is 1. It means if all balls are distributed in a box, they must found somewhere. Is correct, and that is the proof of that term. Thank you.